Hello everyone, my name is Daud Salim. I am a PhD scholar in IIT Mandi. This is a short presentation of our work that has been accepted in JTG IEEE Summer School 2022. This work was carried out jointly with my PhD supervisor, Professor Dr. Satyajit Thakur. The topic is an application of Quasi uniform entropy vectors. The outline of my presentation is introduction, background, main results, conclusion and references. As we know that the convex closure of the entropy vectors for the quasi-uniform random vectors is the same as the closure of entropy region as mentioned in reference 1. And the one-to-one correspondence between quasi-uniform codes and quasi-uniform random vectors has been established in reference 2. The problem was to determine whether a given vector is a quasi-uniform entropic or not. The solution is given in recursive algorithm as mentioned in reference number 3. Another application is to characterize the boundary of the almost entropic region. We have given a novel approach to establish the looseness of known inner bounds for the entropy vectors at the boundary of almost entropic region. For communication models such as network coding, this approach can be applied to design network codes from quasi-uniform entropy vectors. As we know that the entropy vector for the discrete random vector is given as mentioned in equation number 1. The set of all entropy vector is called the entropy region and denoted by gamma n star. One of the central problem in information theory is to characterize the gamma n star. So the random vector xn is a quasi-uniform random vector if for any non-empty subset alpha the x alpha is uniformly distributed over their respective support S alpha as given in equation number 2, and the probability of any event is defined as given in equation number 3. So the problem is to characterize the entropy vector at the boundary of closure of gamma 3 star, and the sub problem is, are the known inner bounds tight or not? So the polyhedral cone, the closure of gamma 3 star can be equivalently represented as the conic hull of the vectors E12, E123 prime, and the definition of gamma 3 in terms of cone is given in equation number 4. So here we show a novel approach using a new quasi-uniform approach that the known inner bounds for the entropy region in the phase first and the phase second are loose. So from the previous literatures, the theorem 1 states that the entropy vectors belongs to a one-dimensional phase if the following constraint in equation number 5 are satisfied, and theorem 2 states that the entropy vectors belongs to a two-dimensional phase if the constraints are satisfied as equation number 6, and the references are mentioned. And theorem 3 states that the entropy vector belongs to the two-dimensional phase if the following constraints are satisfied as given in equation number 7. Proposition 1 states that two entropy vector are in gamma n star, then their summation will also belongs to gamma n star. So here is the first phase denoted by theta, that is cone of E1, E2, E3 and E123 prime can be. So the inner bound for the entropy region in the phase theta can be obtained by proposition 1 and characterization of the entropy vector in the subphase cone EJ and E123 prime, where J belongs to the set containing the elements 1, 2, 3. From theorem 3 we can define that inner bound on the phase theta be the set of all vectors as given in equation number 9 and satisfying the constraint as given in equation number 10. So from all these, the corollary 1 states that the set theta n, that is inner bound on the phase, is an inner bound for the entropy region in theta. And theorem 1 states that there exists a quasi-uniform entropy vectors strictly in the phase theta such that it is not in the inner bound of the phase, that is theta n. And the joint distribution, and this table represents a joint distribution with entropy vectors in theta. So these uh, bullets represent the quasi uniform distribution over x1, x2 and x3. The second phase is denoted by omega, that is cone of E1, E2, E3, E12 and E12 3 prime. So the inner bound for the entropy region in the phase omega can be obtained by the proposition 1 and characterization of the entropy vectors in the subphase, that is cone EI and E12 3 prime, where I contains 1 2 3 and the cone E12 E12 3 prime. From theorem 2 and theorem 3 it is given that we define omega n, that is inner bound of the phase, be the set of all vectors such that equation number 12 are satisfied, and one of the two constraints from equation number 3, 13 and 14 should also be satisfied. So based on these results, the corollary 2 states that the set omega n is an inner bound for the entropy region in omega, and theorem 2 states that there exists an entropy vector in the phase omega such that it is not in the inner bound of the phase omega. Conclusion is, we present a novel approach of utilizing quasi-uniform random vectors and their entropy vectors to show looseness of known inner bounds for the entropy vectors in the boundary of almost entropic region as mentioned in reference 5. The results demonstrate an application of reference 4 to verify quasi-uniform entropy vectors and to obtain a consistent quasi-uniform distribution. The future direction of this work is to explore utilizing the structural property of the target vector for faster verification of quasi-uniformity compared to algorithm number 1 as given in reference 4. So for network communication, this approach can be applied for the network code construction from given quasi-uniform entropy vectors via obtaining quasi-uniform distributions. So this whole work can be obtained on archive as reference number 5 as mentioned in this. Thank you.